Woodman here. It's Sunday, June 16th, 2024. I thank you for listening to this message. I want to talk to you about five postulates of Euclidean geometry and how that affects space time. Euclidean geometry was formulated by the ancient Greek mathematician Euclid, and it's based on five fundamental postulates. The first is that a straight line segment can be drawn joining any 2 points. This postulate states that for any 2 points, there exists a unique straight line segment that will connect the 2 points. Of course, that begs the question, what is a point? But we won't even get into that. The second is that any straight line segment can be extended indefinitely in a straight line. This implies that a straight line segment can be extended beyond its endpoints to form an infinite straight line. In other words, it doesn't end at the 2 points. It could just still keep going on indefinitely out to infinity, right? Given any straight line segment, the circle can be drawn using the segment as a radius and one endpoint as the center. So this postulate ensures that the existence of any circle with a given center and radius is going to basically follow these rules, which we may have learned in middle school and high school. All right angles are congruent. This means that all right angles, 90 degrees, are equal to each other. And remember, congruence is not total equivalence, but it's functional equivalence, right? If a straight line falls on two straight lines and it makes interior angles that on one side that are less than the two right angles, the two lines, if produced indefinitely, meet on that side on which the angles are less than the two right angles. That sounds crazy, doesn't it? I know it does. But this is what's known as the parallel postulate, which essentially states that if two lines are intersected by a third line and the interior angles on one side sum to less than 180 degrees, then the two lines will eventually intersect on that side if extended far enough. Suffice to say that if the lines are truly parallel, they'll never meet. But if the lines are not parallel, they will meet at some point. That's really what that's getting at, but it really became the parallel postulate because the only way you're going to have it be perfect is when they in fact are parallel. Hyperbolic geometry now arose from the exploration of the parallel postulate. For centuries, mathematicians attempted to prove the parallel postulate using the first four postulates, but all attempts failed. This led to the realization that the parallel postulate is not a consequence of the other four, and that new geometries could be constructed by altering or replacing the fifth postulate, which is actually pretty incredible when you think about it. But there are lots of mathematicians who spent thousands of hours working on this, in some cases even years. Some that even went to their graves working on this. But it did lead to new geometries in the future. For example, Carl Friedrich Gauss, Nikolai Ivanovich Lobachevsky, and Janos Bolyai independently developed a consistent geometry that negated the parallel postulate. This new geometry, where the parallel postulate does not hold, became known as hyperbolic geometry. If you kind of look at, say, like that sphere that's in the picture that I have there, this will show you that really there are no parallel lines on that sphere. At some point, those lines will meet back either at one of the poles, right? So this is one type of geometry that's emerged from this, which is like a spherical geometry, right? So yes, you can still have circles and squares and triangles. However, because of the curvature of the plane they're on, they can be curved, negatively curved, which is a hyperbolic plane, rather than a flat plane. And it could also be positively curved as well, which could be like spherical or elliptical and so forth. In circles, in hyperbolic geometry, circles can still be drawn with a center and radius, but their circumference grows exponentially with the radius, which is completely different from the way it would behave in Euclidean geometry. In other words, Euclidean geometry is just one way of looking at things, and it's helpful when you're looking at a completely flat surface that's not curved. But once things curve, things go out the window, like or out the door, and things don't act the way that we would expect them to act based on those lessons we learned in middle school or high school algebra classes. For example, let's take triangles. In hyperbolic geometry, the sum of the angles of a triangle is always less than 180 degrees. This is completely different from what we learned in Euclidean geometry, which is that all the angles of a right triangle have to add, or actually not even right triangle, any triangle have to add up to 180 degrees. And so this is an angle deficit, which is related to the area of the triangle. Um, the more that you stretch the triangle, the more likely that the angles are going to add up to less than 180 degrees. The more that you stretch them outwards, then it could be more than 180 degrees, which is more like that triangle that's on that sphere I'm talking about. And of course, on the flat curvature, they add up to exactly 180 degrees. So the planes that you're drawing these figures on, will impact the rules that apply once you really look at the rules of that particular geometry as to how it's supposed to behave. You're going to find quite different things. So, like I said, in hyperbolic geometry, less than 180 degrees, because you could stretch it out very, very far, but the more you stretch, when those two lines finally meet, that angle is going to be infinitesimally small as you stretch the triangle more and more and more. It's proportional to the area of the triangle, which means that larger triangles have smaller angle sums in hyperbolic space. Now, say we just look at hyperbolic geometry. I'm not even going into spherical or elliptical geometry, but we're just looking at hyperbolic geometry. What would be the fifth postulate for hyperbolic geometry, which would replace our parallel postulate from Euclidean geometry? Well, the equivalent of the fifth postulate in hyperbolic geometry is a statement that through any given point not on a given line, there exists infinitely many lines that do not intersect the given line. This contrasts with the Euclidean parallel postulate, where through any given point not on a line, there's exactly one line that does not intersect the given line. In other words, if you have it where it's truly parallel, then those lines will never meet, right? Those two parallel lines will never meet, although you can have a line that can cross them, but the two lines themselves will never meet. Whereas here, those lines can actually meet, and there's going to be different rules that apply because of that. So remember that Euclidean geometry is based on five postulates, with the fifth being the parallel postulate. Hyperbolic geometry emerged from the realization that altering the parallel postulate leads to a consistent alternative geometry. In hyperbolic geometry, familiar shapes like triangles and circles exist, but they behave far differently due to the negatively curved plane. As you can see in that center figure there, that's what you have when you have like a negative curvature plane. Notably, the angles of hyperbolic triangles add up to less than 180 degrees. The hyperbolic parallel postulate allows for infinitely more parallel lines through any given point, leading to a rich and diverse geometric properties. Whereas if you're dealing with spherical or elliptical, you're going to be dealing with far less parallel lines. How does hyperbolic geometry factor into Einstein's general relativity, which basically theorizes that space is curved, right? So it revolutionized our understanding of gravity, space, and time. In this theory, gravity is not seen as a force between masses, but as a curvature of space-time caused by the presence of mass and energy. This concept of curved spacetime can be understood in terms of non-Euclidean geometry, particularly hyperbolic and elliptical geometries. Try to imagine that you have this flat piece of paper, and then you put this super heavy ball on the paper. The paper doesn't break, it doesn't rip, but it just stretches to accommodate this huge sphere that weighs a lot that's now being placed on top of it. The space of that plane, like that paper, is going to curve around that sphere. So Einstein's field equations describe how matter and energy in the universe influence the curvature of space-time. These equations imply that massive objects like stars and planets cause space-time to curve around them. The greater the mass, the more significant the curvature. So this is what goes on in our universe, is that yes, our universe could be somewhat flat, but then you have these massive bodies like stars and planets and other things. The space time around those objects are going to start to curve. And among those who explore these phenomena, they talk about three different types of curvature, right? The first is positive curvature, which describes a closed, finite universe similar to the surface of a sphere or elliptical geometry. Then you also have the zero curvature school of thought, which corresponds to a flat, infinite universe. And this is more in line with Euclidean geometry, but as we know, that's quite too simple, right? And then you have negative curvature, which describes an open infinite universe with a saddle-shaped curvature, which is the equivalent to hyperbolic geometry, right? And you can see that middle negative curvature object there is like a saddle, right? Hyperbolic geometry is particularly relevant when describing negatively curved time-space or space-time, which can occur in various cosmological models. Because again, we don't always have all the answers, but we have a lot of working theories and things that are accepted by scientific communities as a whole. So what will be the properties of hyperbolic geometry in space-time? Well, again, going back to triangles in hyperbolic space, the angles of the triangle are going to add up to less than 180 degrees. Thus, the larger the area of the triangle, the smaller the sum of its angles. This is because hyperbolic space expands exponentially and the surface becomes saddle-shaped. And going back to again to the parallel line phenomena, unlike in Euclidean space where there's exactly one parallel line through a point not on any given line in hyperbolic space, and that there are infinitely many lines that do not intersect the given line, diverging from each other, where you could have all these different parallel lines, right? Um, that that in of itself is something that really doesn't exist the way it would in Euclidean geometry when you're talking about hyperbolic geometry. So now let's talk about geodesics. The shortest path between 2 points in curved space-time is called a geodesic. In hyperbolic space, geodesics behave differently from straight lines in flat space, often appearing as curves. In other words, we're traveling the best that we can to get from point A to point B, but because the space-time is actually curved, it's not going to fly like a straight line going directly through those points. It's going to actually be like a curved line. What about gravitational lensing? Light follows geodesics in curved space-time. In regions with negative curvature, which are hyperbolic light bends around these massive objects, creating effects like gravitational lensing, where the light from a distant star is bent by the gravity of an intervening galaxy or an intervening cluster of galaxies. So when we look at the cosmological models that predict this, um, in hyperbolic geometry, we use this to model certain cosmological scenarios. For example, what if the universe has an overall negative curvature? It would imply that an open universe will be expanding outwards forever, right? Because you hear that the universe is not fixed, right? That in fact, it's expanding outwards over time. But it can expand outwards in a positively curved or negatively curved universe. If it's positively curved, then at some point it would probably collapse. But in a negatively curved scenario, it could expand outwards indefinitely. What about black holes and singularities? Near a black hole, space-time curvature becomes extremely pronounced. The behavior of objects and light near these regions can be described using hyperbolic geometry. Inside the event horizon of a black hole, space-time curvature leads to a singularity, which is a point where the curvature becomes infinite. That's a mouthful. Detailed explanation of the effects of curved space-time on hyperbolic triangles. In hyperbolic geometry, a triangle's angle, some being less than 180 degrees, has direct implications for space-time. The first is that you have this angle deficit and this corresponding area, right? And so the angle deficit, 180 degrees minus the sum of the angles in hyperbolic triangles, is proportional to the area of the triangle. This relationship helps in understanding the volume and shape of various space-time regions, right? In other words, we have to be able to come up with reliable calculations for this, but how do we do this knowing that space-time doesn't behave exactly the way we predict it would? Curvature and geodesics. In curved space-time, geodesics are not straight lines, but curves that represent the shortest paths between points. In a negatively curved hyperbolic space-time, geodesics are going to diverge more than they would in flat or positively curved space-time. Which brings us back to that fifth postulate again, right? Which is how does the fifth postulate in hyperbolic geometry relate to Einstein's theory of general relativity? In Euclidean geometry, the fifth postulate or parallel postulate states that through a point not on a line, there's exactly one line parallel to the given line. In hyperbolic geometry, this is replaced by the statement that through a point not on a line, there are infinitely many parallel lines. This principle is essential for understanding the geometry of spacetime in general relativity. Multiple geodesics. In hyperbolic spacetime, through any given point, there can be infinitely many geodesics that do not intersect at given geodesic, reflecting the complex nature of, ultimately, space-time curvature. So now, how does that relate to non-intersecting paths? Well, this principle helps explain phenomena where particles or light rays take divergent paths around massive objects, right? Because again, I told you if a massive object is put on a rubber paper that can stretch, then you're going to have that curvature. And so you want to understand the gravitational fields that are operating there and how space-time bends, because that's going to affect your calculations of how light will travel or even objects will travel in that type of a region. So, hyperbolic geometry provides a mathematical framework for understanding negatively curved spacetime in Einstein's theory of general relativity. It helps describe how massive objects curve spacetime, leading to phenomena such as gravitational lensing and the behavior of geodesics. The differences in triangles, parallel lines, and geodesics between Euclidean and hyperbolic geometries illustrate the profound impact of curvature on the structure and behavior of the universe. Let's talk about why space actually curves around large objects, right? Because we said it that happens, but why exactly is that happening? The concept of space curving around large objects is a central tenet of Albert Einstein's theory of general relativity. Why and how this happens? Well, let's go into that. Gravity as curved space-time. Einstein's insight here um, is that he saw something else going on that prior to Einstein, really they looked at a more Newtonian sort of point of view, right? In other words, Isaac Newton described gravity as a force between two masses. But Einstein actually came and proposed that gravity is not a force, but a curvature of space-time caused by mass and energy, right? And so that kind of changed the way we think about these things, right? Because you're always being told that this force that's pulling you, but if it's really just a necessary effect of the curvature of space-time, that's going to affect how things behave. So space-time is the three dimensions plus the fourth dimension being time, and stars and planets can influence how this works. So let's look at the mechanism of curvature. Mass and energy have an influence. According to Einstein's field equations, the presence of mass and energy tells spacetime how to curve. The greater the mass, the more significant the curve. So in other words, going back to that rubber paper example I keep talking about, try to imagine this massive spherical object that's on this rubber paper. That plane is going to keep on stretching and curving, and it's going to affect everything around it. In curved spacetime, the straight line paths or geodesics that objects follow are in fact bent. Objects move along these geodesics, and what we perceive as gravity is actually this curved motion. Whoa, mind blown there, huh? Visualizing curved spacetime. So here's the rubber sheet analogy, right? Which I've mentioned a couple times in this video. A common analogy is to imagine space-time as a stretched rubber sheet. When a heavy object, like a bowling ball, is placed on the sheet, it creates a depression. Smaller objects, like marbles, placed onto the sheet will roll towards the heavy object, which in turn mimics the force that we think is gravitational attraction, but in fact it is a feature of the curvature of space and time. What are the limitations of this analogy? Because, analogies are helpful, but they're not always perfect. So This particular analogy is limited because it only visualizes two dimensions of space and doesn't fully capture the four-dimensional nature of space-time. In other words, how is time being visualized on this particular analogy? It's not, right? So that's a problem, but at least it kind of gives us an idea of what is going on from a very rough viewpoint or standpoint. Let's talk about Einstein's field equations. These complex equations describe how matter and energy in the universe influence the curvature of space time. They are fundamental to predicting how objects move under the influence of gravity. So, um, think of it as like a stress energy tensor. This tensor in Einstein's equations represents the density and the flux of energy and momentum in spacetime. It describes the distribution of mass and energy that ultimately causes curvature. So, what are some examples of curved spacetime? Well, one of the first examples is a pretty obvious one: our solar system. The sun's massive gravitational field curves space-time around it. Planets follow these curved paths, which are elliptical orbits around the sun. In other words, we always wonder, like, okay, if gravity is pulling these objects in, why don't they just collapse in on the sun? Why don't they just all collide, right? And it's not necessarily the case. It actually follows this curved motion of space-time. What about black holes? Extremely dense objects like black holes can create intense curvature as well, to the point where not even light can escape, leading to the phenomenon known as an event horizon. So here, actually, this is the case where you are going to have things being drawn into the center of this massive object, right? Gravitational lensing. Light from distant stars bends as it passes near massive objects, a phenomenon known as gravitational lensing. This effect is evidence of the curvature of space-time itself. Crazy how that works, right? But that's what's going on. Let's look at some experimental evidence. Mercury's orbit. The precession of Mercury's orbit around the sun could not be explained by Newtonian mechanics. It was, however, accurately predicted by general relativity. In other words, Newtonian physics, weren't good at the time that they were created for understanding basic things. But again, the assumptions that they rely on are not enough, and it was Einstein who helped bridge the gap um, through his theory of relativity. Also, think about ripples in space-time, which are caused by accelerating massive objects, like merging black holes. That's another factor that comes into play that's well explained by Einstein's theory of relativity, but not necessarily by Newtonian classical physics. Space curves around large objects due to the influence of their mass and energy on the fabric of space-time, as described by Einstein's theory of general relativity. This curvature really affects the motion of objects and ultimately of light, right? Because light still has to travel. And it leads to phenomena as planetary orbits, black holes, gravitational lensing. This concept really shifts our understanding of gravity from a force to the actual geometric property of space-time, fundamentally altering our view of the universe. In other words, if you go by Euclidean geometry, then yeah, force would be an easy way to explain it. But when you actually understand that there's hyperbolic and elliptical geometries going on, then it can more easily be explained as the way space-time is bent around certain massive or dense objects, right? Um, so the universe itself can be thought of as either being positively curved, flat, or negatively curved. Each type of curvature has distinct implications for the structure and fate of the universe. And we talked about this earlier about whether the universe was infinitely expanding or whether at some point it would actually collapse in on itself. So let's talk about positively curved space-time. Positively curved space-time is often likened to the surface of a sphere. In such a universe, parallel lines eventually converge, and the geometry is closed and finite, right? If you look at that sphere, you will see that to be the case. Triangles itself add up to less than 180 degrees. Parallel lines eventually intersect, which is, I mean, a big no-no in Euclidean geometry, but it can exist in spherical geometry. And the shape of the universe is finite in extent, but unbounded, meaning you could travel in one direction and eventually return to your starting point, right? Because that's what we mean when we say come full circle. What are the implications for the universe? Well, in this would mean that we would be dealing with a closed universe, right? A positively curved universe implies that the universe is closed and may eventually stop expanding and recollapse, leading to a big crunch, right? We heard the universe started with a big bang, but the big crunch is when everything just kind of collapses in and just comes together in this huge crunch. Flat space-time. I mean, this is the easiest way to think of the universe, but it's not necessarily always realistic. But I think our universe is kind of considered to be very close to this. Um, the geometry here is Euclidean, and the universe is infinite and unbounded. The characteristics would be that the angles of a triangle add up to exactly 180 degrees. Parallel lines remain equidistant, and thus they can never intersect. And the shape is infinite and flat. And the implications for the universe would be that you got to reach some sort of critical density. In other words, if the universe is expanding outwards as we believe it to be, which scientists seem to be confirming, then there's going to be a problem with critical density, where the universe can expand forever, but the expansion rate will asymptotically approach zero over an infinite amount of time. In other words, it'll appear to keep expanding, but then there'll be some point where we just don't really see any more differences. It's just there. It's gone too far now. Everything's gone down to zero, right? And then let's talk about the negatively curved scenario. And the negatively curved space-time scenario resembles a saddle shape or hyperbolic geometry. In this type of universe, parallel lines diverge, and the geometry is open and infinite. In terms of characteristics, the angles of a triangle add up to less than 180 degrees. Parallel lines diverge as they extend, and the shape of the universe is infinite and open. The implications for such a universe, based on this negative curvature, is that it's an open universe. A negatively curved open universe implies that it will expand forever at an accelerating rate. And of course, the question is that realistic? That depends on who you talk to, right? The debate is ongoing, right? So let's see what that does for our current understanding of the universe's curvature, which at this point has been debated back and forth between these possibilities. According to the latest observations and measurements, especially those made through the cosmic microwave background, CMB radiation, and if you don't understand what that is, I do have another video that talks about CMB that you can watch. The universe is remarkably flat with only a very slight curvature, if any. Um, the cosmic microwave background provides a snapshot of the early universe. Remember, light takes a long time to travel, so the things that we are seeing are things that have already happened at earlier points in time, but the light took so long to reach us that it's almost like it's going on forever, right? And the universe is probably very close to being flat. It's not perfectly flat, but it might be close to being flat. And so this then eventually led us to believe that there is dark energy, and that in the accelerated expansion of the universe fits well with this flat or nearly flat universe model, that the geometry of space-time is balanced between positive and negative curvature. And so how does that curvature affect the fate of our universe? Well, if the universe is more positively curved, then it will eventually stop expanding and begin to contract, leading to the big crunch, which we mentioned earlier. On the flip side, if it is more flat, then it could indefinitely expand outwards, uh, but the rate of expansion will decline over time, where we approach a stable size over an infinite amount of time, and it will just appear like we're not even expanding at all. It's not that we're not expanding, but it's just that the rate has become so minuscule, it actually approaches zero. And then in the negatively curved open universe, we have this negatively curved universe that will expand forever, with galaxies moving far away from each other at an ever increasing rate due to the influence of dark energy. Would we ever get to see all that? Well, that may take a lot of time to see. So I don't know if we'll see that in our lifetimes, but perhaps our successor generations will get to see that, if that in fact was indeed the case. In conclusion, the curvature of space-time can be positively curved, flat, or negatively curved, each with unique geometric properties and implications for the universe's fate. Current evidence suggests that our universe is nearly flat, which affects how it will continue to expand and evolve. Understanding the curvature of space-time helps us to comprehend the universe's large-scale structure and ultimate destiny. I hope that you've enjoyed this message. I know this was actually a pretty long one compared to the videos I normally do on this channel. This is definitely over half an hour at this point, but I really hope that you stayed tuned and you enjoyed the entirety of this message. If you're new here, you're welcome. This is a safe space. We welcome you aboard. If you're returning, I appreciate you so much. I love you. Your support of this channel is what keeps this thing going. Please don't forget to like, share, and subscribe. I love you. I love you. I love you. Have a wonderful and blessed Father's Day. Take care. Bye.